Welcome back to part 2 of our study on integrals, at least our initial study on integrals. Right now what we're doing is we're evaluating what's known as a finite integral. That basically means that there's actually an answer. There's actually an area answer. Yes, there'll be some problems we do where there's not actually an area answer, but we'll be doing those in the next chapter. And those are called indefinite integrals. Now, I hope that you realize that we're using area techniques, like area formulas. Yeah, you should know the area of a rectangle and a triangle and a circle. So will you see a circle though? Okay, well, that's yet to be determined when we go over our next problem. But let me just mention that every problem we do is visual. Every problem we do is visual. You need to participate. You need to look at these, whether you look at them on your calculator or for some of them, we're just going to sketch them without a calculator. But yeah, that's why students seem to like this topic, because it's visual and you're drawing some sketches, and then we're going to whip out some area formulas. So how about this? The integral of negative the square root of 9 minus x squared from 0 to 3. All right, well, like I just said, it's visual. So type it in your calculator. Make sure you do this because I want to know if you're able to see the area that this problem is describing. Okay, yeah, now when you type this in your calculator and you graph it, you end up getting this little guy. Sort of looks like a smiley. Not really a smiley face, but it definitely looks like somebody that's smiling. It's a semicircle. Okay, we want to recognize that shape that came from that formula is 1/2 of a circle. But do you realize that we don't need all of this? Do you realize that we only need the part from 0 to 3? This is important when you guys start doing these problems on your own, that you realize where the area is. And in this case, it's only that little quarter of a circle, isn't it? It's just a quarter of a circle. And so we're starting to come up with a strategy on how we would ultimately solve this problem. I hope that strategy involves thinking about this region from 0 to 3. By the way, when you do these problems on your own, you will show a sketch. That is part of showing your work. And we identify that we're looking for this area here. I hope that you would say that it's a quarter of a circle that has a radius of 3. And so, of course, we're getting ourselves a little bit closer to an actual answer, because we just need to do a quarter of pi r squared, a quarter of pi 3 squared. So it looks like 9 pi over 4, doesn't it? And that would be my answer. Except it's wrong. What? I thought it was a quarter of a circle. We only look from 0 to 3. But yeah, 9 pi over 4 is wrong. Do you know why? Somebody would know. Is it you? Yes, that's correct. It is under the x-axis. Remember what we learned on our last lesson, that if you're under the x-axis, it's negative area. So yeah, we need to throw a negative sign in front of this 9 pi over 4. Okay, and this is an example that when we found our answer using geometry, nothing really negative came out of it. We just need to know. We have to see that area is under the x-axis. All right, so negative 9 pi over 4. Ready to take a look at another one? I do mean it that you would want to take a look at this. Now, this is the absolute value. It's the integral of the absolute value of x minus 1 from -2 to 5. I don't know if we need to be too quick to put this in our calculator. If you do want to put it in your calculator, you're going to have to find the absolute value command. It's in the math menu. And then you scroll over to num, and you'll find the absolute value command. I thought that this would be a good time just to remember that when you're graphing a function that has a transformation, of -1, that just means that the function shifted to the right one. And so we have a vertex at 1, 0. And you should know that the absolute value graph is going to be this common V shape. The other reason I like talking about this one a little more without a calculator is because we can continue to analyze for the important parts of this graph. That is, we can continue to analyze for the x values of -2 to 5, and of course the corresponding y values. If you just plug in -2, you're going to get -2, 3. And if you plug in 5, you're going to get 5, 4. Now, do we realize where the area is? I kind of got a little bit ahead of myself, but do we realize that the area is sort of constrained by these points that are on this absolute value graph? So yeah, we're looking for this triangle right here, and okay, yeah, and we're looking for the area of this triangle here. Okay, so as you can see, we're kind of dividing up the shape, but we're basically just dividing up into two triangles, but both of them have a base and a height. And of course, you can think about those dimensions by just thinking about how much we've moved in the x. I hope you would say that the base or the x movement is just 3. And then we've got this y movement. We already determined that to be, it's also 3. So we've got 1/2 base times height. Looks like it's 9/2. And then, are you thinking about that green area over there? You should be. Just another base and a height. Should have got a base of 4, and it looks like a height of 4. So we end up with another isosceles right triangle, but it's still going to be 1/2 of that 4 times 4. So of course we end up with an area of 8. All right, and I would expect that you're going to add these together. If you'd like to make a common denominator, you can think of that 8 as really 16 over 2. That way you can add 16 and 9 to be 25 over 2. And of course, is that our final answer? Well, yes, it is. Both of these areas are above the x-axis. It's fine that we had 2 of them found separately. Also want you to realize that that yellow triangle was kind of over in like a negative x value. That's fine. There's nothing wrong with being in a negative area. And then that green triangle was kind of in like a positive. But both areas come out to be positive. It doesn't matter what the x values are for each of those triangles. So we have 25 halves. Notice the problem's visual. All of these problems are visual, and they require a sketch. If we were in class, I would put this one up on the board, and I would say, check it out. Check it out a little bit more without too much guidance from the teacher. So we're trying to find the integral of 2x plus 6 from -5 to 2. All right, how'd you do? Okay, maybe you graph -2x or 2x plus 6 on your calculator. Maybe you're just thinking a little bit about the y equals mx plus b. Of course, a y-intercept of 6, and then a rise over run of 2. So we end up with a nice little straight line. Okay, but where's -5? Where's -5? Okay, it's probably, yeah, gotta give myself a little more space here. -5 is probably out around here. And where's 2? Okay, maybe it's only right there. Okay, we got to start to see these areas. The area is always between the graph and the x-axis. So yeah, we have a triangle that's actually below the x-axis right here, and then we have another triangle that's above the x-axis. Now, you know, there's actually a point that we haven't found yet that turns out to be maybe the most important point on this for this particular problem. Okay, and you'll learn that as we do more problems that the x-intercept is very, very important. The x-intercept. Now, maybe you can see the x-intercept on your calculator, but think about plugging a 0 in for y into this equation. You also would be able to confirm that the x-intercept is at -3. Now that x-intercept is pretty important because that's going to help us to determine some dimensions for our triangle, isn't it? And it's also the place where the positive and negative area changes. We'll continue to talk about that as we go through this chapter. All right, you should have been plugging in -5. If you plug in -5 into the equation, you get -4. And if you plug in 2, you end up with 10. And of course, those y values are pretty helpful when it comes to thinking about the dimension of your triangle. This guy's going to have a dimension of 4 or -4, if you want to call it that. This is going to have a base of 2. So we have our dimensions of that one. And again, the x-intercept, I know I didn't draw it to scale very well, but the x-intercept helps us to see that that dimension is 5, and this dimension is 10, of course, based on that, that y value. Okay, now, when you find your areas, yes, 1/2 base times height, but remember that this one has to come out negative. Okay, so we can just make it negative. And then my other triangle, well, it's got a base of 5 and a height of 10. So we end up with a half of 50. So I guess that comes out to 25. Okay, so when I'm finding my answer, we haven't seen a problem like this. When I'm finding my answer, I do need to take the net areas. So I do need to take the negative and I do need to take the positive so that I can come up with a net area of 21. Okay, and that 21 would also be my final answer for my integral. But again, I can't emphasize enough that we subdivided. We'll be using that term a lot more, and notice that we subdivided with the x-intercept. All right. Hey, one more problem, and it's kind of special because it's not a typo. It's the integral of 3x from a to 2a. So it seems like our limits of integration are variables. Okay, well, here. It shouldn't be too scary. We should be able to graph 3x. That's your calculator. It's just a line. It's got a slope of 3. A. Okay, I think it should say that a is a positive number. That seems to be a little bit missing from the problem. So we've got a in a positive place, and then 2a. Are we starting to see these areas? Okay, again, the area has to go, of course, between the graph and the x-axis. So we're going to be looking at this space right here. Now that shape, we could divide it up. We could divide it up into a triangle and a rectangle, just like we did in our last lesson. But I want to make sure that you guys know that we also could use we could think of this shape as a trapezoid. It's not normally the way we see a trapezoid. Normally that trapezoid would have been turned 90 degrees because we need 2 parallel sides. And we do have that. It's both of the red sides. So do you remember the area of a trapezoid? It tends to be one that I don't remember either. Here it is. It's 1/2 h. And then here we have the sum of our 2 parallel sides, S1 plus S2. It's going to be a helpful formula for this problem. It'll also help us, since we won't need to divide this up, we can just straight up plug into this formula for h, which is the perpendicular x distance. Okay, again, it's the height, but it's like the perpendicular x distance, and then the parallel sides are always S1 and S2, and those are the y lengths. So, are you ready to plug in to the trapezoid formula? I guess we need to find these dimensions first, don't we? So it would be expected that you would find the this x distance. This again is the same as the height, but it's just the distance between a and 2a, so we can call that a. And then it looks like we're going to need to get these parallel sides. So can I plug into my formula? Can I plug in 2a? Yeah, you can plug 2a in. That's going to come out to be 6a. which would be your y value, which would also be your height. And I can plug in a, and again, that would just give me 3a, which of course is that parallel side. Okay, so I've got what I need. Just kind of trust the formula. The area of a trapezoid, once again, is 1/2 the height. That's going to be a. And then the sum of those sides, 3a plus 6a. Oh, I can actually do that math. I can make that become 9a. So we end up with a over 2 times 9a, which if we keep doing some math there, I think we end up with 9a squared over 2. Okay, that would be your integral. It's in terms of a, since my limits of integration were in terms of a. As a final thought for our lesson 5.2, I'd like to have a conversation with you about a very interesting integral. It's actually the integral of the sine of x. Now remember, the sine of x is that up and down periodic graph, and it has an interesting area, specifically if we look from just 0 to pi. And that area you're going to discover is 2. Now what we're going to do is we're going to look in the book on page 264 and continue this conversation, but eventually you're going to do a little exit ticket out of this. So it'd be helpful for you to have your book open and know that I'm going to go over some of the initial examples, but you will finish the remaining for a small grade. All right, now if you look on page 264, you'll see there in that box that they do indeed tell you that the integral of the sine of x from 0 to pi is 2. But let's make sure you understand where that is and just specifically what that is referring to. It does show you in the book, but it can be helpful to see it on your own calculator or take a look at mine. I brought it along. Here's the sine of x. It is that common graph. But now that we're in calculus, we're going to be kind of noticing some new things about this graph, specifically from 0 to pi. We're going to notice that this area, that is this area under one bump, is actually just equal to 2. Now we're going to take that as a given, and we're going to use that to find some other areas that are connected to this space or this interval from 0 to pi, but indeed would be new. Are you ready? You can see them in your book. The first one there is the integral of the sine of x from pi to 2 pi. Now, if you have your calculator still on, it's still the same sine wave, but I want to make sure that you're looking at it at the right spot. And indeed, you should be looking from pi to 2 pi. So now we're talking about this space. Now, it's still the area of one of these bumps, isn't it? So what's going to be different? That's right, it's going to be negative. So it's still 2, but of course it's negative 2 because it's now under the x-axis. See how this works? We're going to take what we're given and we're going to use that to come up with some new areas. How about the area from 0 to 2 pi? Okay, now this time we're taking the full sweep from 0 all the way over to 2 pi. So we're taking the positive with the negative, aren't we? Technically, we would end up with 2 and negative 2. Yes, they cancel out to be 0. Yes, we end up with an integral or an area equal to 0. I'm going to do one more with you. It's going to be number 3. And this time it's the integral from 0 to pi over 2. Again, if you have this on your calculator, you can continue to look at it. Some people do like to draw sketches, especially when it comes time to do this for a little grade. You do have to have knowledge of where pi over 2 is. Pi over 2 is going to be halfway. That's a little hint, isn't it? Halfway in this first bump. So we're looking at just this piece. Well, of course, if the whole bump is equal to 2, and we've only traveled halfway through that interval, then it would reason to think that this one is going to be half of 2, which is 1. And indeed it is. Now, for the problems that you're going to do, I would say that you may not have 100% certainty of the answer. You might have 99% certainty, but there's a piece to this exit where you're trying to just make a conjecture. You're trying to make an educated observation. And I do know that a couple of them, when it's all said and done, especially near the end, that students sometimes are like, I don't know. And so what you're going to do is you're going to give us your best thought. I also want to say that you're not permitted to find these answers using other techniques. What other techniques could there be? Maybe using something on your calculator, maybe like a program or a special button. I would just say kindly that you want to experience the thought process behind these. You want to look at the graph, you want to see where that bump has gone, and then you want to take what you know, which is that the area is 2, and figure out how you can connect that to your new area. All right, so we're going to make a little exit ticket out of the remaining questions. I believe it's 4 through 9. If you count carefully, there are 4, 5, 6, 7, 8, 9. That's 6 problems, and it's only worth 5 points. So I even give you one that you can get wrong, and it won't be counted against you. Okay, so the first one here is number 4. It's the integral of 2 plus sine from 0 to pi. Now, type that in your calculator, but I want you to know that I'm going to give you a little hint on this one. I would have given it to you if we had been in class anyway. We want to make sure that you're getting off to the right start. Okay, 0 to pi of this graph. Okay, definitely we're talking about this region right here, which does include the top part, the bump as we're calling it, but it also includes this region down here, which kind of looks like a rectangle, doesn't it? So a little tricky here for the first problem, but you're going to take what you know and you're going to connect that to that rectangle that I showed you, and you're ready to go. All right, so problems 4 through 9 as an exit ticket.